Okay, I think we'll go ahead and get started. Thanks everybody for coming. My name is Patrick Van Fleet. I'm the chair of the Department of Math and director of the Center for Applied Math. This is our first colloquium in the spring 2017 semester. We'll have one more in February and we'll have two in April, so you can check the website, stthomas.edu/cam for the talk dates. Today is a really exciting day for all of us at St. Thomas, especially in the math department. We're welcoming back an alum. Dr. Sam Stechmann is a UST grad from 2003, triple major, math, chemistry, and physics. Yeah. And if you look at his CV, he puts math first, which is really, really nice, so we appreciate that here even more. After graduating from St. Thomas, Sam went on to Crown Institute in New York and earned his PhD in 2008, and from there he went on and did a postdoc at UCLA, was funded by ONR, remember correctly?
For the postdoc?
Yeah, part of it?
NOAA and NSF.
NOAA and NSF, I'm sorry. You got ONR funding later, didn't you? Okay. So anyway, Sam is now an associate professor at Wisconsin. Continues to be a phenomenally strong researcher. Been funded by several agencies. I think the last grant was, what, $750,000, is that right? From National Science Foundation for his research, just a little one there to help along with his work. Anyway, we're very happy to have him here. So please join me in welcoming Professor Stechmann.
Thank you very much, and thanks a lot for having me. It's great to be back and to see everyone again. There we go. So the topic of the presentation is mathematics of weather and climate prediction, and I kind of moved into this when I got into graduate school. I was in graduate school in a mathematics program, but all of my research was related to atmospheric science and weather and climate. And I guess the starting point is what you see every day. I guess you see this weather forecast for what's going to happen in the next few days, what's going to be the temperature, the highs and the lows for a few days in advance, and also things that you probably don't look at as much, like the wind speed and things like that. And if you really want to know details, amazingly, you can now get hourly data on a lot of websites. You can see what's going to happen every hour of the day, so you'll know exactly when the rain's coming. And when you see this type of thing, they present it so nicely for you that you really have no idea what's going on behind the scenes. And so I guess the question is, how in the world do we actually predict the weather? And in the end, it's more or less two big components that are put together. One piece is a huge computer simulation where the entire world's atmosphere is divided up into little chunks, kind of like pixels in an image. And you need to know the wind speed, the temperature, the pressure, the amount of liquid water, and everything like that for every one of these little pixels. And the second thing is observational data. And that's going to play a role of helping give us the initial conditions we need to march forward in time and predict what's going to happen in the future. And lots of other math in there too. Okay, so I guess in this talk I'm going to try to talk about both history, where are we coming from, and also what are some of the modern challenges today in weather prediction and climate prediction. So let's start maybe with how and when did weather forecasting actually begin? And one place where you could say it started in some sense is back in 1904, a man named Wilhelm Bjerknes. He said in a paper that in principle we could take the laws of physics and cast them as an initial value problem for differential equations. And this would be one useful set of differential equations for that task. And the corresponding physical law is listed over here on the right. So the first equation describes conservation of mass, the actual mass of the gas of the atmosphere. And so the density is this rho variable right here, and u is the wind speed. This second equation describes conservation of momentum. And there's a pressure gradient force right here. Rho times g pointing downward, that's gravity, pulling the atmosphere towards the Earth. And on the right, this is a viscosity term. and then a few thermodynamics equations. There's the ideal gas law. It's written in a slightly different form than you're maybe used to seeing. You're maybe used to seeing PV equals nRT. In atmospheric science, we usually use density rho instead of volume V. And we need an equation to define an entropy. And then we have the second law of thermodynamics, which describes how the entropy of the atmosphere evolves in time. And you may remember that entropy is either conserved or increasing. What can cause the entropy to change is if there's a source, like clouds can provide a source of entropy in this situation here. That's one of the sources, Q dot over here. So in the end, this is 7 equations. If you notice that this velocity has 3 components. There's an east-west component U, there's a north-south component V, and then the up-down, up towards space and down towards the Earth component W. So there's 7 equations and 7 unknowns. If we could only just solve these equations, then we could predict the weather. I mean, this is 1904. I mean, there's no such things as computers right now. And there's also very little observational data. So how do you even know what the atmosphere looks like right now in order to predict what's going to happen in the future? So this was a bit of a crazy idea at the time. And in 1922, a mathematician named Richardson came along, and the situation wasn't a whole lot better. There's still no computers, and there's still very little observational data. But this guy says, well, let's just give it a try anyway. So he's trying to predict the weather over the area of Germany. The result was actually really horrible, which is maybe not surprising because he doesn't have any computers and he has very little observational data. So some details about what happened. He was just trying to predict the weather 6 hours in advance, given some observational data that he had. And no computers. He did these calculations by hand. So if you remember, like in your first calculus class, when you compute derivatives as rise over run, he's basically doing rise over run on those equations over all of Germany by hand. It took him about a month, several months to complete this work by himself to try to predict the weather 6 hours later. So this is not exactly a useful forecast at the moment. And it didn't work, even though it took that long. But his vision for the future was that we could have a whole room full of people all helping to do these calculations, and then maybe we could do a 6-hour forecast in 3 or 4 hours, maybe. And maybe just a few side notes about this Richardson guy. If you take a numerical analysis class here, you might hear of Richardson for things like Richardson extrapolation and Richardson iteration. So he was a pretty influential mathematician in his day. Okay, so we need more stuff. We need more resources if we're going to actually get to real weather predictions. It's just not happening in the early 1900s. So one of the key things was what are called radiosondes. And they're called this because it's basically a weather balloon, but the name comes from radio, meaning that's how it transmitted the data back to the Earth. This little balloon has a whole bunch of things connected to it, like a thermometer and things like that. And it's going to rise up into the atmosphere, and every now and then it's going to measure the temperature and radio that signal back down to the surface. And this was a huge breakthrough for collecting data, because before this time, all you knew was the temperature at the surface. And that's not good enough. If you want to predict the 3-dimensional evolution of the atmosphere, you really need to know 3-dimensional data about the temperature at different altitudes in the atmosphere. And so in 1940, there were 334 stations worldwide. And you can see that there's pretty good coverage over the US and a little bit over Europe, but there's huge parts of the globe where there is just no data at all. Over the oceans, there's none, and over areas like South America and Australia, there's not really much either. And at these places where there's a red dot, they have regularly timed observations every 12 or 24 hours. And over time, more and more stations were added in until it's starting to become feasible that we can get a good picture of what's going on with the weather all over the globe. So in 1965, there were about 1,000 stations all over the globe. And they've spread all over to interesting places. Like Antarctica now has weather stations all over. Lots of little places, little islands over the oceans are giving some data over the oceans, although things are still very sparse over the oceans, and most of the data is clustered over the places where there's populations. And as a function of time, this is the number of weather stations by year, and you can see how things gradually increase, and then things start to decrease, just out of curiosity. Does anyone happen to have a guess for why they started to decrease? And I guess the timing isn't perfect to an event that I'd be thinking about. So the reason they started decreasing is because they're actually getting a lot of the data from satellites now. Because satellites will give you data over the oceans where you can't get it from the station data. The timing's a little off because the first satellites were in the 60s. The first weather satellites did not start coming into being at least more regularly until the 70s. When I use data, I usually start trusting it around 1980. That's when satellite procedures were very well established. Okay, so we've got the data now. And so around 1950, the second ingredient is coming into being now too. So the first computers were starting to be built. And yet again, a mathematician was at the forefront of this, John von Neumann. And he was working with an atmospheric scientist named Jules Charny. And they were the ones who did the first numerical weather prediction on an electronic computer. And so they for the first time had a computer, and this giant thing on the wall is just one computer. And this is John von Neumann right here. And they had all the observational data they needed. And what I haven't told you about is a lot of the math that had to go into this too, because it's really more than just having a computer and having the data. But just for comparison, to see what his first computer was like. His computer was called ENIAC, and I wish I could remember what that acronym stands for, but I can't right now. And if you compare that computer from 1946 to a typical computer from, say, 2006, from 2006, you can do about 20 billion operations per second. His computer could do about 5,000. The power use is absolutely phenomenal. It only takes 31 watts now. It took 170,000 watts to do the same amount of work before. The weight was 28 tons before. It took up her whole room. And now all of that takes up a weight that's essentially negligible. The size now, this is about, is that about 10, that's about 10 millimeter by 10 millimeter? Yeah, so it's about a square centimeter now, one chip. Everything from that room now fits on just one little chip. And now we have transistors as the basis for our computers, whereas back then, each one of these little vacuum tubes was playing the role of a transistor. And this first computer cost about $500,000 to make, whereas now computers are a heck of a lot cheaper. So at the time, though, this was absolutely amazing to be able to have a computer that could do these calculations so Richardson doesn't have to do them by himself. And now I guess the question is, what was all the mathematics that went into these types of predictions? So I'll mention just a few. There's a lot more than this, but these are some simple ones that come to mind. So one piece gets back to how computer simulations use discrete space and time. So we said that it's breaking up the entire globe into little pixels. It has to do the same thing in time. So it's marching forward in time with a fixed time step. And for the space step, you'd like to use a really small one, but computational resources are going to limit how small of a pixel size you can use. And for the time step, there's some really cool math theory behind how you can choose it. You're not allowed to just pick whatever time step you want. There is a theorem which goes back to three guys, Courant, Friedrichs, and Louis, from 1928, in fact, before computers, actually. And John von Neumann actually did some other work along these lines, too, to demonstrate what time step is needed. And the simple version of this theory says the following. It says your time step is restricted. Your time step must be smaller than the space step divided by the maximum wind speed that you're seeing in your simulation. So as a couple of examples, if you have a grid spacing of 10 miles, and that you might start thinking 10 miles isn't very small. And if you're going to simulate the weather or the climate over the whole globe, 10 kilometers is actually something that can get used sometimes, or 10 miles. And in this case, take a wind speed, say, of 40 miles per hour just as a typical number, and you're now restricted. You have to take time steps of less than 15 minutes. If you try to step forward in time longer than 15 minutes, you're actually going to have problems. You're going to have instability. Your computer simulation won't work. And it actually takes math theory, a theorem, to prove that this is needed in order for your simulation to actually work. And as another example, for some types of weather prediction simulations, you can use smaller grid spacing of about a half mile or so. And in these cases, you're now using a time step, marching forward in time about 1 minute every step. Another example, I guess, whether you want to call this math or computer science, I guess, is up for debate. But this is regarding a woman named Grace Hopper. In terms of popular science, she often gets stated as the person who found the first computer bug. And so if you remember that big, giant computer that took up a whole room, she found an actual bug, which she taped to her work log. It was a moth. And so people often claim this was the first computer bug, and this is where the word came from. But it actually, people were using the term bug much earlier in all sorts of other machines and other applications. But it's fun. It's a fun story. But she's also very famous because she invented the first compiler. So if you've ever written your own computer code, you know that you write down all your commands, and then you have to either push a button or type a command in to create an executable file. She's the first person to ever create a compiler that turns your words, if this, then do this. She was the first person to ever write something that could turn those English words into a computer program. This is a picture of her back in 1960 at one of the early computers from the era. She also went on to help develop some of the first programming languages like COBOL and had an influence on some other ones like Fortran. And this is a picture of her in her later years as a rear admiral in the Navy. Okay, so where did things go from there? Over the years, there have been kind of evolving frontiers. So at these times, these older times, weather prediction was the new thing, and that stayed true for quite a while. It still is true. There's still a lot of work to be done. But when I talk about the frontier, I kind of mean what is the new thing that people are trying for the first time. They're the pioneers in their field. So back in the 50s to the 70s, people were making weather predictions, the first ones ever done on computers. And it took into the 80s and 90s before people were able to start making climate predictions. And this was harder just because for climate, you need to simulate the atmosphere over the entire globe. It's not going to be enough to just simulate the atmosphere over, say, the United States by itself. So we needed more computational power before we could try to start doing simulations over the whole globe for climate. And now there's a new frontier. It's kind of at the intersection of weather and climate. So now the question is, can I predict the weather or climate a couple of weeks or a couple of months in advance to know what is next summer going to be like, or what's next winter going to be like? Will there be more snow? Will it be colder than normal? And things like that. And for instance, just to illustrate how this is a hot topic right now, the National Academy of Science had a report on this topic. They call it intra-seasonal and interannual climate prediction. So intra meaning within, so within a season or within a year. How do you predict things on those timescales? And interestingly, this development was actually foreseen by John von Neumann back in 1955. So I just want to show you some clips from that paper of his. So he wrote a paper, the Atomic Energy Commission, he was with the Atomic Energy Commission, on some remarks on the problem of forecasting climatic fluctuations, where he said, in considering the prediction problem, it's convenient to divide the motions of the atmosphere in 3 different categories. And it kind of depends on the time scale of the prediction. The first category would be where things are determined by the initial conditions. And that's the weather prediction stuff that we were just talking about. In a second category, you're at the opposite extreme, where motions are essentially independent of the initial condition. And the reason you can think that is because climate is about what happened averaged over a year or a decade or something like that. So it doesn't necessarily matter where you started from, because after a little while you forgot where you came from. And what happens over a whole year doesn't really matter where things were when they started necessarily. And in between these 2 extremes, there's another category. The problem of forecasting over periods from 30 to 180 days, say, how the end of a season or the beginning of the next season will look. That would fall into this third category. And so his vision in 1955 is that we were going to need to first try short-range forecasts. That seems like the simplest problem to try. We're given an initial condition. How do we evolve our equations forward in time? And then secondly, he thought long-range forecasts, meaning climate predictions, would be the next easiest thing to try. And then only finally would we be able to attempt the medium-long time periods. And he's describing here how different methods are going to be needed for each of these 3 different classes of problems. And that is more or less how things have evolved, at least in terms of the frontier. The new frontiers have evolved in kind of the way that he has foreseen, but there are always still remaining big questions to be addressed. So the rest of the talk will kind of organize around this vision. So right now we've been in the weather prediction category, and we've been talking a lot about history. So I guess one question is, what are some modern challenges? What is difficult today in improving our weather forecast still? There was a really nice paper a couple of years ago that laid out summaries of some of these problems. And the paper was called "The Quiet Revolution of Numerical Weather Prediction," and I really like this title because it really feels like the way we view weather predictions. You know, we take it for granted. We see these weather predictions every single day, but we really take for granted all the science and engineering breakthroughs that have gone into this over an entire century. So just to summarize the article, they say that advances in numerical weather prediction, they represent a quiet revolution because they've resulted from a steady accumulation of scientific knowledge and technical advances over many years. And with only a few exceptions, have not been associated with the aura of some fundamental physics breakthrough. There have been some exceptions, but mostly it's just been steady, continual progress over the years. Nevertheless, the impact of numerical weather prediction is among the greatest of any area of science. I mean, it is absolutely amazing that we can predict the weather in the way that we do every single day, actually several times per day. As a computational problem, global weather prediction is comparable to the simulation of the human brain and the evolution of the early universe, and it's performed every single day at major operational centers across the world. And this graph from their paper illustrates how this has progressed over time. So this is showing forecast skill on the y-axis and years from about 1981 to roughly the present day. And the different colors are different lead times of the forecast. So the blue one here is for a 3-day forecast, trying to predict 3 days in advance, and 5 days in advance and 7 days for the yellow. So just as one comparison, think about a 5-day forecast in 2013 or today and how much you trust that. That is sitting up here right about there. And that is roughly comparable to a 3-day forecast from 1983. So things are steadily improving, just slowly sloping upward and always getting better. And one other interesting thing is just the north versus the southern hemisphere skill. You'll notice that that's the 2 different blue colors, for instance. Predictions in the northern hemisphere were more accurate for a very long time than in the southern hemisphere. And then right around 2000 or 2001, they came together. And this actually had to do with some of the algorithms and some of the math that went into things that changed in that year. And they were able to better use the data that was available and improve the forecast. Another big component of these forecasts today is modern supercomputers. So this is what a supercomputer looks like today, or this is what a small chunk of a supercomputer looks like that can fit within the view of our camera. So just for some perspective, John von Neumann's entire computer now takes up about that much area within one of these little rows in this giant rack. So this whole supercomputer right here is like having 72,000 of John von Neumann's computers. And what this has meant is that algorithms have needed to change. Because in the early days with von Neumann's computer, there was what's called the serial approach to doing algorithms. You have a bunch of instructions that you want to process. You hand them to this processor one by one, and it just keeps working through them sequentially or serially. But now with supercomputers, we have a whole bunch of different processors that all are going to have to work together at the same time to try to reach their goal. So a strategy would be take your n instructions, send them to n different processors. Give one instruction to each processor. So up here, it's passing a different instruction to a different processor. And this is going to lead to a dramatic increase in our computer speed overall, even though the speed of one processor itself doesn't necessarily have to increase for this to work. So the old challenge, when you had algorithms of the serial approach, your goal was you wanted the fewest number of steps in your algorithm. And so if you just want an example of what do I mean by an algorithm, think about the problem of, suppose I hand you 10 numbers, and I want to know what is the biggest number in this collection. And so in order to figure that out, you have to think about, well, how would you work through all of the data to try to figure that out? Or you could think of a harder problem. What if I gave you 10 numbers and I wanted you to sort them in increasing order? How many steps would it take you to get those numbers into increasing order? So thinking only about the number of steps in the algorithm, that was always the old way to do things when you had one computer to work with. But now things have changed when you have the parallel approach. Because it used to be that the bottleneck was how fast your computer could process the information. But now, with the parallel approach, one thing that can slow you down is communication. These different computers have to communicate with each other. They each have a different piece of memory. So these numbers that I gave you, some of them are getting passed to one computer. Some of those numbers are getting passed to another. And so one part of the algorithm that can slow things down is, if I want to compare my number with another computer's number, we have to talk. And we have to pass information between each other. And that can now become the bottleneck when you have 72,000 computers trying to talk to each other. So an ideal situation to try to think about for algorithms now is, how can I write an algorithm with the least amount of communication? I'll assume that my processing speed is really, really fast, and the thing I want to avoid is talking between the processors. This completely changes the way that you would write algorithms, because now the bottleneck is just accessing memory or communicating information. Yet another challenge is what's known as data assimilation. And what this gets into is, how do we create the initial conditions for our forecast? So this is a flow chart for numerical weather prediction. And I guess the part we can start with is over here, creating the forecast. There's a model that we're going to run, and we're going to march forward in time to tell you what happens in one day, march forward, what are we predicting will happen in 2 days, and so on. In order to start that whole process, we need to tell it our best guess of what the weather looks like today. And in order to do that, we need to combine our two sources of information about what today's weather looks like. And this process of combining that information is called data assimilation. We're assimilating observational data and model data together. So we want the best initial conditions by combining info partly from observational data. You know, we have weather balloons, satellites, and things like that, which give us information. And partly from, go back to yesterday. Yesterday, we created a one-day forecast, our guess of what today's weather would look like. That is another piece of information for us for what today's weather is. Both of these pieces of information contain errors. There's measurement errors, and there's errors in yesterday's one-day forecast as well, because forecasts aren't perfect. So the idea here is to try to figure out how much weight do I want to give to each of these two contributing factors in order to minimize the overall error. And so this might remind you of problems from calculus, where you're given a function and you need to minimize it. But what makes this really hard is that there's 10 to the 9 variables. There's like 1 billion variables we're talking about. We're talking about the error in the temperature here in St. Paul, the error in Wisconsin, the error in the temperature in Massachusetts, all over the globe if you're doing a global forecast. So how do you do, and you remember going to Calc 3 and you did minimization problems with 3 variables maybe, or 2. This is a minimization problem with 10 to the 9 variables. So one of the big challenges that still remains is how do you combine these two together? And there's other approaches out there that don't necessarily lean completely as a minimization problem, but this is one interesting way to view it. Trying to minimize the errors for your initial condition. Yet another challenge, this has been something that has only come up in really modern times, and it's probabilistic forecasts and uncertainty. So with increasing computer power, what we've been able to do is not just do one forecast of what tomorrow's weather will look like, but we can do 10 or 100 forecasts to see what it'll look like. So what we do is we say, well, I have this initial condition. And on the previous slide, we were saying, I don't know the initial condition. I don't know what the weather looks like today. There's errors in this initial condition. So why don't we consider an ensemble of initial conditions? Each one is the starting point of these different lines. And sometimes this type of plot is called a spaghetti plot. And so you assume that each one of these is a plausible state of the atmosphere today. Run a simulation forward in time. They will give you different forecasts of what will happen tomorrow with the weather. So this is an example. Each one of these is a different picture of Britain, and the colors are showing the precipitation that each forecast believes there will be over Britain. And then you can combine all of these different ones to come up with a probability of precipitation at every location, because some models will say it's going to rain here, but others won't. I guess, in fact, it looks like about 90% of them said it's going to rain here tomorrow. They seem to be agreeing there's no rain in this area. But then other areas, there's some uncertainty as to whether it will or will not rain. And that uncertainty comes from the different answers that these different forecasts gave. While this idea might seem simple, it's actually really hard, because it looks like, oh, well, you're just perturbing this. You just bump it around a little bit in each of these directions. But remember, this is a problem with 1 billion variables. So you have to try to figure out, how do you perturb this initial condition? Do I assume that my temperature was a little bit off in Minnesota, a little bit more off in Wisconsin, a little more off in Iowa? Like, was I too high, too low? And we only have enough computational power to do perturbations in about 10, maybe 100 different directions. So one really tough problem is to figure out, when I create these different perturbed initial conditions, what are the best directions to use? What are the important perturbations to make? Okay, So that brings us to the end of our weather prediction segment. And these last two will be a little bit shorter because they're a little more modern. And also because a lot of the problems that came in weather prediction are also still there for climate prediction, for instance. A lot of the same principles are being used, but not necessarily all of them. So now next up, let's think about climate prediction a little bit. And so one of the big changes now is we don't necessarily want to know the temperature everywhere, at every detailed location, at every city in Minnesota. What we're thinking about now is climate. We're thinking long-term, and we're thinking about global averages. So the simplest question to ask about is, if I average the temperature over the entire globe at every location, what is it? And if you just look at data, so this is not a prediction, this is looking just at available data of the global temperature over about 100 years or so. And you can see it increases in the temperature over that time, and also at the same time increases in carbon dioxide concentration. Okay. But now for predictions. So each one of these acronyms is a different weather and climate center in a different country around the world. So for instance, CCCMA, that's one in Canada. CSIRO, this one is in Australia. Hadley Center is in Europe. GFDL is in Princeton. MPI is in Hamburg, Germany. And NCAR, these are in Boulder, Colorado. So each one of these centers, they maintain their own climate prediction model. They probably have their own supercomputer on site dedicated to problems like this. And they all are running their own model and trying to predict what will the global average temperature be over the next few decades. And what you'll notice is they're not agreeing. They more or less agree that things will be warming, but they're giving slightly different answers as to precisely the temperature of the warming. And so you might rightly wonder, why are they different? Which one's right? But in the end, we have to remember there's not necessarily a right answer here. There's errors and uncertainty all over in these problems based on the data, based on the model itself. So the goal is to try to understand how much can we trust our answer and how much uncertainty is there in the answer. So just to give a run through of different sources of errors in these predictions, this is a very physicsy classification of where the sources are, not necessarily describing the errors in the mathematical formulation. Although in the end, the two go hand in hand, because every one of these physical processes is represented by math equations in the model. So if we go down to the bottom, they're quantifying, it says radiative forcing. You can think about that more or less as being increase in temperature, whether it's positive or negative. And on average, the models are predicting about a 1.5 degrees of warming. And this is all given some scenario of how much carbon dioxide we're putting into the atmosphere in the future. But what you'll notice is the error bar on that estimate is pretty big, plus or minus about 1 degree. Well, I guess these aren't degrees, these are watts per meter squared. Plus or minus about 1 watt per meter squared. And what you'll notice is if you look up at these individual sources of the errors, this uncertainty here is largely contributed by this one row. And this is the uncertainty due to clouds and aerosol. And this is one of the trickiest parts of climate prediction. The basic principles, like the greenhouse effect and things like that, usually you don't account for clouds when you start thinking about the greenhouse effect. But clouds can significantly alter the radiative balance of the Earth. Clouds can block the sun's rays. They can reflect the sun's rays back into space, possibly cooling the Earth. On the other hand, clouds themselves can act like a greenhouse thing because clouds are absorbing. The Earth is trying to radiate an infrared energy to try to cool itself. But clouds in the atmosphere can absorb it, just like carbon dioxide does. So there's these competing effects of clouds. Clouds can potentially warm the Earth if they act like a greenhouse type of a thing, or they can reflect the sun's rays and possibly cool the Earth. All of those different models have different ways of handling clouds in math form. And they were all giving, and that's one of the greatest sources of the spread here in their different predictions. So one major uncertainty into the future is trying to better understand clouds and aerosols. How can we represent them mathematically in these weather and climate prediction models? So just to summarize that, a lot of this is somewhat historical. So at the moment, there is scientific consensus in terms of the Intergovernmental Panel on Climate Change, who have shown evidence that global average temperatures have increased in the past, and they are predicted to continue increasing based on our best climate prediction models right now. There's many remaining questions, because this was all about global average temperatures for the moment. But as you've probably thought about yourselves, you start to wonder, how much does the global average temperature matter for me or for any particular application you care about, whether it's agriculture, extreme events, hurricanes, and things like that. So a lot of the remaining questions revolve around further details and impacts on humans. So one of them, for instance, is clouds and climate feedback. How can we reduce that uncertainty due to clouds? And another one would be, how are rainfall and extreme events going to change into the future? So besides just global average temperature, is there going to be more rain, less rain, more intense rain, more extreme rain, and things like that? So just to give one example of some work in this direction, and this is actually some of my own work in a paper that just appeared a couple of weeks ago. So what we have here is many graphs showing the distribution of rain event sizes. So by an event size, we mean like how much rain fell in a rain gauge or a bucket, measured in inches or centimeters, or in this case, we're using millimeters, in one event, from when it starts raining to when it stops. And what you'll notice is that small events are the most likely. Just sounds reasonable. The strongest, heaviest rain events are less likely. And what's interesting is there is a size of events when things really start to become unlikely. They just don't happen as much. So there's sort of a cutoff where the type of distribution changes to being quite unlikely. We actually have a simple mathematical model that created these nice smooth curves up here. We can work it out with pencil and paper, what those curves look like in the top. And that theory matches both observational data, and now also, on this slide, we're showing model from the climate model, or data from the climate models as well. And what's really interesting about the climate model data, you'll notice that each one of these colors, there's two curves. One of them is not actually a climate prediction. One of them is based on the last several decades, the historical. And then the other plot of the same color is from a prediction into the future. So what we're seeing is that both of these curves still essentially follow the mathematical theory up here, but that cutoff has shifted to larger events. So the largest event that you might think you'll see has become even larger into the future with global warming, based on our climate models at the moment. So it's, in some sense, you could maybe summarize it by saying the largest rain events are going to be even larger in the future. Okay, and this brings us to the last piece, the kind of middle ground. So this is the intersection of weather and climate. How do we predict things on scales of weeks to months and things like that? So one name this goes by is extended range forecasting, and in some ways it's the modern frontier. These things are just being tried for the first time over the last couple of decades. And we have to, before we get going on this, we have to lower our expectations here. I mean, we're not going to be able to say what the temperature is going to be in St. Paul on June 1st of 2017. If we're going to predict the weather that far in advance, we're only going to be able to predict averages. And so one way to think about this is shown by this graph. If you're going to predict the weather, say, 1 day in advance, you could maybe predict the average over 1 day. If you're going to try to predict the weather 1 week in advance, maybe all you'll be able to do is predict the average temperature over that week. So as you try to predict things farther and farther in advance, you're probably going to have to settle for in average over a longer period of time. And so in order to make this work, what we really need are weather and climate phenomena that vary on these timescales. Is there any weather phenomena or climate phenomena that goes up and down on timescales of weeks and months? Because if you can find those things, then that's what you could hope to use to make these predictions. And a couple of candidates, one is El Nino. Have you heard of El Nino? Yeah, so you hear about it a little bit in Wisconsin. If you lived in California, you would hear about it all the time. It has a major impact on the western part of the US, a little bit less so in the Midwest. And another one is the Madden-Julian oscillation, which I'll tell you about a little bit now. So what is this thing, the MJO? It's named after two guys named Madden and Julian. They discovered it back in 1971. And again, there was some pretty cool math involved to make this discovery. So back in 1971, several interesting things came together for the first time. So for one thing, they had pretty good computers at that time. For another thing, they had the right data. You know, we showed earlier that you were starting to see weather stations on islands during the mid-1900s. These guys had finally 10 years of data at an island in the middle of the Pacific, and nobody had really looked at it very much yet. And they used a new algorithm called the fast Fourier transform. So this algorithm made it possible to study what was a very long time series at the time. And this algorithm was developed by Cooley and Tukey in 1965, although it appears that Gauss knew about it, as he knew about pretty much everything, you know, a long, long time ago. And this is the cartoon they drew of what the Madden-Julian oscillation is. I'll show a little bit of a more quantitative version here. So this is a statistical composite of what the MJO is. You'll notice each one of these 8 panels is a map. You can see the outline of, like, you can see Africa and Somalia here. This is the tip of India and Southeastern Asia. And then over here, Central America and South America. And you'll notice that there is this big blob that moves eastward as we move from one panel to the next. So this blob is a huge area of clouds and rain that is slowly moving to the east near this equatorial region. This thing is absolutely huge. It has a wavelength that's in the ballpark of half the circumference of the Earth. It has an oscillation period of about a month or two. So if you knew how this thing was behaving, you could potentially use that to predict weather and climate a few weeks in advance or maybe even a month in advance. And this slide kind of hides the complexity of this thing. It has a detailed multi-scale structure to it. So that was a statistical composite. This is the real thing. So this is longitude near the Indian Ocean and Pacific Ocean. Time is going down for several months. This is November, December, January, February. And you can see this blob of clouds moving slowly eastward over a time scale of a month or two. And you can see that within it, it's not like it's one huge cloud. It's a whole bunch of cloud clusters and things like that grouped together. And so one illustration of how you can use this type of thing for weather prediction, or how we hope to use it, is, and this is again a second example of some of my own research. We have a mathematical model. It's a stochastic model for the MJO. And on the left, this is a piece of our motivation. So one piece of the MJO that I haven't shown you yet is how it's not always there. It's not like the MJO is just always there going up and down. It comes and it goes. And that's what makes it so hard to predict. So this is one example with time going up for several months, September, October, November. And you'll see that there was no MJO for a couple of months. And there was one event, a second event, a third one, nothing really happening, and then another. So we wanted to try to design a model that would look like the MJO and also capture this type of behavior. And this is just one of the pictures from our output, where you can see that it's quiet for a while, and then you see a few red moving blobs and quiet again. And I'm sorry that I don't have enough time to tell you a little more about this model. But this model, it's intermediate in complexity between So this model, we call it the skeleton model because it captures just the skeleton or the crudest features of the MJO. In form, it's a partial differential equation, and it only uses one spatial dimension, only longitude. The rest of the structure is kind of built in. So because it has only one spatial dimension, it's way cheaper to do simulations with it than if you were using a big global climate model, which is very expensive. And then a third category, there are actually other models out there that are even less expensive. It's like ordinary differential equations, like 2 variables or 3 variables, for instance. And what's really interesting from past results, so this is showing the skill at predicting the MJO. The dashed lines are climate models, really expensive models. The solid line is a statistical model. It's one of these cheap low-order models. And what you'll notice here is that the correlation or the skill as a function of forecast day is roughly the same, whether you use a supercomputer to simulate the climate all over the globe or whether you use some really inexpensive little model. So there's comparable skill for these cases. And the other thing that's a little disheartening is that they're only skillful out to about 15 or 20 days. And we were saying this thing at timescales of a month or 2. So we were hoping, that you could predict this thing farther into the future. So this is just to illustrate, there's motivation for better understanding of tropical clouds and rainfall. We still don't quite understand clouds and rainfall at the level that we should. And what we're hoping to do with our model is to try to use it to make predictions like this as well, and hopefully we can have improved forecast skill with our model. And just one last slide about the MJO. So I was showing you how everything works in the tropics, that the MJO is tropical, but it has global impacts. So in the tropics, one interesting thing is that it modulates hurricanes and tropical cyclones. So this blob, within one phase of it, there's hurricanes and tropical cyclones. In the other phase, where it's clear skies, it's unlikely that there's going to be hurricanes and tropical cyclones. And it also can excite different types of waves that can come up and affect weather on the west coast of the US and California and Oregon and places like that. So it has a global impact even though it's a tropical phenomenon. Okay, so just to summarize, we've talked about some of the mathematics involved in weather and climate prediction, both history and some of the modern challenges. And you can kind of break this down into 3 different categories. And in some of the early history, there were some prominent mathematicians who played a role, like Richardson, von Neumann, Grace Hopper, Courant, Cooley, and Tukey. And some of the modern challenges include supercomputers at the heart of a lot of these problems, trying to understand uncertainties in the forecasts and involving probability into the forecasts, trying to understand how to model clouds and rainfall, and then the modern frontier of making extended range predictions of the weather and climate a few weeks or a few months in advance. And there's a lot of room here for mathematicians to contribute and help improve our weather and climate forecasts. So that's it. Thanks a lot for your attention.
So with the MJOs, so currently the MJOs are not incorporated into the global climate models?
Yeah, good question. I wanted to include a slide or 2 on that. So, right, you would expect that they would be in the model and simulated well and doing well. This is actually one thing that climate models struggle with. They struggle with the tropics. And the reason is that, think about the summertime here in Minnesota. What is the rain like in the summer? It's scattered thunderstorms. If it's the fall or the winter time, things come through more smoothly. It's a little easier to predict. That scattered thunderstorm weather, that's the tropics every day. So trying to predict rain and clouds in the tropics is a real challenge, especially when your pixel size is a little bit too big to be actually resolving the clouds. So one of the big challenges is definitely just trying to get your model to have a good MJO in it. And that could be one of the reasons why the expensive supercomputer simulation only does as well as the really cheap model.
With
They do, although they are decreasing in numbers. And I've actually heard that they're expensive. You have to have a person manning them right now. They are automated to some degree. And there are really interesting research questions out there to ask which of these sources of data and observations are most important. Which of them reduce the error in our initial conditions the most? And so like over the oceans, the satellites are absolutely needed. So maybe I should mention one trade-off. So I keep talking, satellites are great, but one thing that satellites struggle with is the vertical dimension of things. They don't quite give the vertical dimension like these weather balloons do. So that's one reason why one advantage of the weather balloons.
Was the Coron-Friedrichs-Lewy condition motivated by their attempt to understand the failure of Richardson's prediction?
Oh, good question. No, I think they were in 1928. What they were doing is they were thinking about existence and uniqueness of solutions to PDEs, and they were looking at discrete forms of the equations to try to prove these things. And so they found that in order for the discrete solution to converge to an actual continuous solution of the PDEs, they needed this condition. And as far as I know, it was not motivated by what Richardson was doing. That would be interesting if it were. Yeah, I don't know. I don't think so, though.
One other question. So, with the change of initial value, sometimes you might get chaotic behavior.
Yeah, there is definitely chaotic behavior in here to some degree, although it's quite a different system, because a lot of times when we think about chaotic behavior, it's with really low dimensional systems, like 3 or 4 or 5 or 10 degrees of freedom. Here the system is also very turbulent, and so any of the chaotic behavior is also messed up with a whole lot of very turbulent high Reynolds number dynamics too. So it's all it's a little bit tricky to sort out the types of chaos that we're familiar with from simple math examples in such a high dimensional system. Oh, that's a good question. So I guess if you want to predict where the pollution will move to and things like that, that does make it a harder math problem. You have a new variable. You have to keep track of the concentration of smoke or the concentration of whatever type of chemical it is you're trying to keep track of. Yeah, and that's also really difficult because a lot of times the source of this thing is a smokestack, but we're using a pixel width in our model that's pretty big. So that can definitely be a lot trickier. And another thing that comes to mind, I guess maybe it doesn't happen so much with, I'm not sure how much it happens with the pollution, but with clouds, sometimes the satellite observations are impacted by having a cloud in the way. Sometimes they're not. So that was just one other thought that came to mind about how things like that can get in the way of satellite observations.
All right, please join me in thanking I think I know what Gauss is thinking. Okay. Yeah. He did. He